Often, science fiction plays a role in inspiring others to learn more about astronomy and space. So, who here is a Star Wars fan? If you can raise your hand, or if you know anything about Star Wars.
Here on older new Star Wars.
I'm a personal fan of the old, but
Yeah.
I grew
I'll,
up into the new one.
I'll put my hand up for the old ones.
Okay. All right. So, who here has seen the iconic scene of Luke Skywalker looking into the sunset of the two setting suns? The older generation probably most likely seen it. So, what do you call a system of two stars? This is a pretty maybe high advance, but it's in the name. Double star system, close. It's called a binary star system. Binary star system, I think. Okay. Our next final trivia question is about what are the names of some subatomic particles? You can just list them or go into classification if you'd like. Just even elementary school basic like names. Yep. All right. We got proton, neutron, electron. Yep. Okay, so Dr. Ocha, is that correct, sir?
Yeah, you can just call me Rui if you want.
Dr.
The best.
Dr. Wu will be discussing another subatomic particle about which plays a key part in understanding the universe. With that, Anu?
Adrian, you didn't get a chance to introduce yourself yet, so would you like to introduce yourself?
Yeah. I'm Adrian, and I'm a rising sophomore at Rockridge High School in Virginia. I'm super excited to learn about today's topic and I'm looking forward to Dr. Ojha's presentation. I'll be monitoring the chat along with Kieran. If you have any questions while Dr. Ojha is speaking, please type them in the chat. At the end of the session, we will have a Q&A. Kieran and I will read the questions you have in the chat so that Dr. Ojha may answer them. Thank you.
Okay. All right. So for those who have just joined us, welcome. This is our first of 4 seminars in the coming Sundays, and all of them will be at 5 p.m. Today's seminar focuses on finding the sky secrets over centuries leading to the present golden age in astronomy, when telescopes can see all kinds of light. We're excited to invite Dr. Roopesh Ojha to give today's seminar. Dr. Ojha grew up in the shadow of the Himalayas and has followed his childhood interest in astronomy to the ends of the earth. He came to Boston on a scholarship after studying at University of Pune in India, also known as the Oxford of the East. Dr. Ojha completed his PhD at Brandeis University in Massachusetts, studying relativistic jets powered by supermassive black holes, using a technique that combines radio telescopes scattered all over the globe. He worked at the Harvard-Smithsonian Center for Astrophysics, operating a sub-millimeter telescope at the South Pole, and has also worked at the Australia Telescope National Facility in Sydney, as well as the United States Naval Observatory in Washington, D.C., and the Goddard Space Center in Greenbelt, Maryland. He is currently a program scientist at NASA headquarters. Dr. Ojha, we are honored to have you with us today, and welcome.
Thanks very much for those kind words. Thanks everyone for being here. My goal in what remains of the hour is to share with you my great sense of almost unreality of being in a dream, to be alive at a time when there's been a fundamental shift. Okay, actually I should, as I talk, let me also go back to sharing. Okay, so you guys are probably used to hearing people say things like, oh, this is an amazing time in history, etc., to the point where it's almost a cliche, right? But as I hope to be able to show you in this talk, these superlatives are extremely applicable to the world of astrophysics, to the world of astronomy, and we really are living through a revolution. That's what And in the introduction, Anu talked about, and Anu said that I would be talking about many different kinds of light. That is true. But we are living, for the first time since 2014 and 2015, respectively, we have gone beyond studying the universe with light. We now have other ways of studying the universe, two specific new ways of studying the universe. One is via a particle called the neutrino, which we've now learned to detect. And the other one is because since 2015, we are pretty confident in our detection of gravitational waves. Neither of these two messengers are light. So we've gone beyond light for the first time in human history. And that's why I call this a revolution. And that's why the title of my talk, that's what the multi-messenger means. Since as long as we've been humans, we've been curious about the sky. And everything we've learned about the sky has been through the study of light. Okay. And instead of you asking me a question, let me ask a question. What I just said is not entirely accurate. Can anyone tell me? So I said, throughout human history, everything we learned about the universe has been through the medium of one form of light or the other. There is one small but important exception to that. I'll let you think about it. I'll ask you at the end if you can think of what the exception to that statement is. It's mostly true, but not entirely true. Okay, now it would be good if I could move my slide forward. Doesn't seem to want to go forward. It works. Okay, great. So I don't have to cover everything here, but this is the sort of design of my talk, right? I'm going to tell you a little bit about my role. I'll tell you a little bit about who I am, because that always helps set the context. Though Anu's already done a great job introducing me, so I can skip past that very fast. Then I'll talk a little bit about what neutrinos are, how they were detected, a little bit about gravitational waves, what they are, how they were detected. I'll tell you why you should care, and then end with what I started, which is introducing you to new senses that humanity has acquired very recently. So the first point over there is an important one to make. We started today with trivia, which basically tested your knowledge of facts. It used to be true until quite recently that a big part of my job when I gave a talk was to convey facts. Nowadays, because of the easy availability of high bandwidth internet, the easy availability of very high quality information that's at the fingertips of almost anybody, right? The role of speakers like me has changed in a subtle but very important way. We still deliver some facts, but that's not really important. Because, for example, at the end of today's talk, if you want to find out more about neutrinos, you can easily go and do that, right? And the important role that I can play is context. Okay, what I can do is point you in the direction of what I think is important. So the role, I mean, me telling you what is the highest peak in Antarctica is something, it's almost useless, because you can easily Google that and find out which is the highest peak, right? But me giving you an idea of what the transantarctic range is like, the kind of research done there, that is what I'm useful for. So it's more about context, less about facts. Okay, now because Anu has already given me a pretty good introduction, I'll just show you a few photos, because we all like looking at photos. So on the top left here, in the foreground, the green part with the little dots, it's a little bit not as good resolution as it should be. That's a town called Darjeeling. Those of you who like tea have probably heard of it, because the slopes below it are world famous for their tea. And the mountain in the background is Kanchenjunga, which is the third highest peak in the world. The top right picture is a close-up of Kanchenjunga. I grew up in Darjeeling. This peak, Kanchenjunga, is, as the crow flies, about 50 miles due north of my bathroom window. That's what I saw when I was brushing my teeth in the morning. So it's very hard to impress me with mountain views. I think you can understand why. The bottom right is an example of the tea slopes that were below the ridge of Darjeeling. So that's something I saw when I walked to school every morning, right? You have these mostly ladies with these wicker work baskets on their back, and they pick that. When you pluck tea, you usually just pluck the top, right? That's what we call a tea garden. And then on the bottom left is the school where I studied. Wonderful place. St. Joseph's, also known as North Point. Okay, this is a picture of Pune University, which was where I was fortunate enough to do my master's. Some extremely wonderful teachers then and now, as far as I know. And then I got a scholarship and came to, I guess don't have a picture of Brandeis University, but that's okay because Brandeis University is a great university, but the buildings are not, they're modern buildings. They're kind of ugly. They're not really as impressive to look at. But I just wanted to show you a typical example of what I studied for my PhD, right? So this is what's called an active galaxy. So as all of you know, we live in a galaxy called the Milky Way. The Milky Way, fortunately for us, because otherwise our life might not have been possible, is what's called a quiet galaxy. It's peaceful, it's relaxed, right? It's happily getting along. These galaxies, active galaxies, the main difference is in our galaxy, like the Milky Way, almost all of the light that you're seeing is produced by nuclear fusion in the cores of stars, right? In active galaxies like this, the stars are there, right? But the total output of light from the stars, it sort of gets drowned by light produced by matter falling into a central black hole, which is enormous. It's called a supermassive black hole, which means that it has a mass somewhere between 1 million and 1 billion times the mass of our sun. Okay. And in many of these active galactic nuclei, what you see is, for reasons that are not completely understood, though we have some pretty good ideas, some of the matter that's infalling is formed into a pair of jets. And along the axis of the black hole spinning, black holes are usually spinning, right? And they go along the axis of spin in both directions, okay? Now, if you look at this picture from I don't know if you can see my cursor. Can you, Anu?
Yes, we can.
Okay, so this bright thing, and then you can see this coming down to the bottom left. That's one of the jets, right? Now, the other jet should be from here to here, but you don't see it, do you? You don't see anything there. And that's because these jets are moving very close to the speed of light. And one of the effects of that, one of the relativistic effects of that, is that the jet that's moving towards you, towards us, the observer, its luminosity gets boosted, so it's easy to see it. But by the same factor, the jet that's moving away from you, it gets deboosted, so it becomes really faint. And that's why you tend to see only one jet, and you don't see the other one, except in some rare cases when the whole thing is in the plane of the sky. So then you can see both, right? So that's what I studied, and I think I'll leave it at that. Just wanted to give you an idea. Oh, I should say that the technique, what attracted me to this was not the science of active galactic nuclei, but also I just totally love the technique where a single radio dish does not have the resolution. So I'll try and explain. A resolution is basically the ability to see detail, right? So the better the resolution means the smaller the detail you can see. These objects are very far away, and if you took a radio dish, no matter how big you made it, it wouldn't give you the resolution to be able to see this amount of detail. But back in the 70s, actually probably late 60s, people figured out how to combine information from multiple telescopes, right? And there's some neat mathematical tricks that allow you to, and if you have a good enough clock, you need a very, very good clock, right? You can combine information from multiple telescopes, and they can be as far apart as you like, right? As Anu correctly said, it can be, spread across the globe. In fact, I mean, I routinely use telescopes that are scattered. So for Southern Hemisphere observations, I routinely use telescopes that are scattered across Australia, and then there's one in New Zealand, there's one in South Africa, and at the moment it's not working, but there used to be one on the edge of Antarctica. So you can put them as far apart as you like, right? There's no real physical constraint to it. In fact, for a while, the Japanese had put a radio dish in space, so you could actually have baselines going out to space. And basically, the further away you put them, the more resolution you have. Okay, it's not the easiest technique in the world, but it works. And when I first heard about it, I thought it was magic. How do you do this? It's like witchcraft. And even after I understand how it's done, it still feels like witchcraft. So it's a fun thing to be doing, right? Okay, as Anu indicated, okay, I should keep track of the time. Okay, no, I'm not doing too badly. Okay, so as Anu indicated, I had the great pleasure that my first job after getting my PhD was operating a sub-millimeter telescope, in Antarctica. The scientific goal was to study transitions of the neutral carbon. That's the fourth most common atom in the universe. And in particular, at that resolution, my group was trying to study regions where young stars are born. So I used to joke that I was a pediatrician for stars, stellar pediatrician. This was probably, unfortunately, it doesn't look like I'm going to get to go to space. Hopefully that I'm wrong, but I mean, at the moment, it doesn't look like it. So this is the closest I'm likely to get to living in a place that felt like being on another planet. I think many of you are aware of this, that an entire year at the South Pole, in terms of sunrise and sunset, is basically like one day. So you have a period where of maybe 5 months or so, 5.5 months, when the sun never sets, right? It just traces what looks like a circle. It's actually a spiral, but very, very small angle. And for about 5.5 months or so, it's always continuous daylight, and then you have a very slow sunset, and then it's another 5.5 months of continuous darkness, and then you get a very long dawn, and then it comes back. So it's a very strange place, and it's a very interesting place. And I don't want to take too much time. You can always ask me questions about it. Of course, all of you know that it's very cold, and you can't really show any skin. I learned that the hard way. I went there the first summer I went down there. I got a bit of frostbite on my cheek very quickly. So I learned my lesson. You don't expose your skin even in the summer. Of course, in the winter, it's even more challenging. One of the most difficult things to do is to breathe properly, because the air, you don't really want to expose your nasal passage completely, but the air has to get in somehow. So people have different ways of dealing with this. I had this Darth Vader-like, construction that protected my nose and allowed the air through. You can see more or less what it's like. It's not perfect, but it works. And I should mention that apart from being cold, what very few people realize is that the South Pole is one of the driest places in the world. It's drier than the Sahara Desert, which is the main reason why the submillimeter telescope was built there. Because even if there's a little bit of moisture in the atmosphere, it tends to interfere to absorb submillimeter radiation coming through the atmosphere. By the way, this photo shows not very good sky, right? You can see there's a whiteout because the wind has whipped up the snow. You pretty much never get snowfall at the South Pole, right? It's completely dry. So when you see this, what's happening is you have a wind that's blowing down. I mean, it's coming down. It's called a katabatic wind. And katabatic is just a fancy word for gravity driven. So it's almost like you take a jar of milk and pour it down a hill, and the milk comes flowing down, right? So in this case, the wind comes flowing down and it raises the snow. Because at the South Pole, you're standing on something like 2.5 kilometers of snow, right? There's land, but the land is buried under like a lot of ice. And the top layer, of course, has some loose snow on it. So when a wind comes blowing, it just raises everything. Now, this is pretty rare. And the reason why if I showed you photos of my South Pole, you see a lot of these is because when the weather is good, you're working, you're really busy. So it's only when the weather is bad that everybody has time to go and get their cameras and try to take a few photos. So it's a little bit biased, right? You tend to see photos of when the weather is bad, and you don't realize that that's actually very rare. Okay, I think that's enough. I just wanted to show you that in those days, our living quarters were in this geodesic dome. It's called the Amundsen Scott South Pole Station. This is now retired. There's a brand new, very fancy looking building now, which I don't have a picture of. And then I can't resist telling you guys, right, that unlike the North Pole, which of course, as you know, is on water, the South Pole is on land. And so there's actually a pole. So this is my buddy. And if you can see my cursor, this is the pole. This is the actual location of the pole. And you can't quite see it, but there's an American flag over here. And then there's this signboard here, right? Now, couple more things before I tell you more about this. This ice cap you're on is moving laterally. It's moving sideways about something like 8.5 meters per year. Okay. So on January 1st every year, the exact location of the South Pole is remeasured, and you put in a new pole every year. So if you look carefully beneath my friend's elbow, you can see the pole from the year before. And, there's a sort of a roughly, it's not exactly linear, but it's close to a line of these poles marching back, because back to the time when they first started putting them, which was around 1974 or so. So there's a whole bunch of them, right? And if you are on the South Pole, if you're at the South Pole on New Year's Day, then you get to have your name carved on the bottom of this cap over here. So I've got my name on 3 of these. Also, like, I should briefly mention that if you look carefully, you see a silver colored trailer over here. That's my telescope. That's the telescope. And there are some other telescopes in that area. There's about a kilometer between the dome where we lived and the telescopes, right? And that was my commute. And it's probably the best commute, the most interesting commute I'll ever have in my life. That's a close-up of the telescope. This was a proof of concept. So it's relatively small, 1.7 meters. In case you're wondering how these decisions are made, the reason why it's 1.7 meters is because that's the largest thing you can fit into a Hercules C-130 aircraft without needing to disassemble it, okay? Because to begin with, we didn't want to try to build something there. We wanted to take the whole mirror and set it up and run it. Since then, since we tested out all the materials and and I can tell you about those adventures at some point, we learned how to do this properly. So now there is actually a 10-meter telescope with the rather boring name South Pole Telescope. You can look it up. That's the successor to this guy. This guy is retired and has been removed. Okay. After that, I briefly was in Australia. I will move on. I can always tell you, this is the Australia Telescope Compact Array in the desert, like sort of in New South Wales, Western New South Wales. Spent many a happy hour there. And that is a picture of the Naval Observatory, which is in Washington, D.C. Most people know it nowadays as the residence of the vice president. But I mean, she's just in one small area. It's primarily an observatory, and it does a lot of things. For example, it keeps the time for the United States. We have an array of atomic clocks there, and it does a bunch of other things. I can explain my role to you later if you like. Then in 2008, NASA launched a gamma ray space telescope. This is the famous picture from Cape Kennedy. There's a funny story about this. The principal investigator, the launch was delayed because of bad weather. So the chief scientists who had designed this, they had left already because they had only had so much time, and they had committed to be in Japan. They were in Tokyo at a conference, and they were watching this launch, and what they saw was let's see, I have to get this right. Oh yeah. So they could hear the commentary, and they heard the person counting down, 9, 8, 7, 6, and we have takeoff. They heard the commentary saying we have takeoff, and the rocket was still sitting there not doing anything. So everyone was really disappointed because they thought something had gone wrong. But actually what had happened is there was a delay between the visual feed and the sound feed. The launch had actually gone as completely normally, but like because of the delay, they thought that something was wrong and the rocket hadn't taken off. Anyway, so now let me get quickly to what I'm talking about, right? This is just a collage, if you will, if you look at the top left, I picked that one. That's obviously from Egyptian mythology, right? But you can pick similar examples from all of the ancient peoples, whether it's in China, whether it's in India. And everyone was curious about this guy. Everyone realized that there was some connection, at least between the sun and their lives, right? Because their crop circles, etc., depended very much on the seasons, and people were able to link. People were very observant. They were able to link the times of rising and setting of different stars, and people have very good imaginations, so people made up lots of nice stories. And one of the things I find fascinating is how different cultures have all these really neat stories, right, about what's going on in the sky. And also people have very interesting explanations for relatively rare but quite scary phenomenon such as solar eclipses and lunar eclipses, right? I love this story. There's a well-recorded story of two groups of people who are having a battle. This was in the Middle East. I'll remember the name in a second. And in the middle of their battle, while they were busy fighting each other, there was a solar eclipse. And both sides were so terrified, they just stopped fighting and they just sort of froze, because the typical location, you'll be lucky if you see one solar eclipse in your lifetime, right? Today we can travel, we know where the eclipses are, and so on and so forth. So yeah, they were terrifying phenomenon, and people came up with very ingenious explanations for what was going on, right? So I don't know about you, but the part of India I grew up in, the story that we were told about solar eclipses is that the god Hanuman had swallowed the sun. And then the explanation for why the eclipse ended is because his mother scolded him and made him spit out the sun. Okay, so that was the story I was told. I grew up with. But there are other stories. Even in India, there are many different stories. So, and then that, this naked eye observations of the sky was what informed us about the sky, all the way until you get to about 1630. And you see this guy, you recognize him, I think. His name is Galileo Galilei. He did not invent the telescope, but he appears to be the first guy who realized that it could be used to study the sky. And when he did, he made all sorts of amazing discoveries, right? Like, so he discovered the 4 big moons of Jupiter, for example. And philosophically, this was a huge challenge because up to that point, most people believed, there were exceptions always, but most people believed that, everything had to, they had never seen objects rotating on another body other than, the sun, right? So philosophically, it was challenging. Also, like when he pointed to the moon, he saw what we now know are craters and other features on the moon. And that was shocking to people because they thought of the moon as being perfect and completely smooth. And to them, like, this was like a great shock. So he made a number of discoveries, and you could say that in many ways, modern astronomy, observational astronomy, started with him, right? Then to the right of that, you see these 2 guys, that's father and son, and he's one of the fathers of radio astronomy. That was the next kind of light that humans, became good at observing. And down here is a radio telescope. It doesn't look like what most people think a telescope should look like, but but that's because the light waves behave very differently at different wavelengths. So you need completely different kinds of technology to be able to observe them. And very quickly, this is I couldn't resist putting a picture of my satellite as if I own it. This is the Fermi Gamma Ray Space Telescope. That's up there right now, about 550 kilometers above you. I can send you a website if you don't know already, where you can track pretty much any satellite, right? And you can tell where it is at a given time. And I remember I asked you guys to think about what is the one method other than light that humanity has traditionally studied universe. Hint, look at this picture on the bottom left. And let's see if you can give me an answer later. Okay, now what did I do?
We have about 15 minutes.
Thank you. Okay, so I'll get quickly to my point, right? Remember what I said, my most important job here is not to tell you facts, but give you the context. So hopefully you're getting the context of why what I'm about to say is exciting. So I love this plot. I didn't make it. I would love to take credit for it, but I didn't make it. It was made by a colleague of mine. And from left to right, it shows you all the different kinds of light, right? From left to right, it's increasing energy, which corresponds to increasing frequency. And it's the opposite, frequency and wavelength are inversely related. And if you don't understand that, don't worry about it. It's not that important. So if you look, and then do you see these white lines, which are colorful over here? What they are showing you is which of these kinds of light can come through our atmosphere. Because our atmosphere is great at blocking most kinds of light, right? So if you go to the left, you can see that very low radio frequencies, they don't get through very well, okay? But these radio frequencies, starting from around here to up here into the microwave, they can get through pretty well. You can see that's why we have a bunch of radio telescopes on the ground. Then if you move up into the, in between, this is the sub-millimeter range. There used to be, it's now retired, there used to be a telescope on a plane called Sophia. And so, they come some ways into the atmosphere. So if you fly high enough, you can see them, right? So, and then infrared doesn't get through very much at all. And then, of course, you come to the visible part of the spectrum. And that's what we can see with our eyes, which also means that it gets through, right? And we can have a whole talk, because it's very interesting to think in terms of evolution, right? Why our eyes evolved to be sensitive to that wavelength range and not any other wavelength range, right? And how, and then a question that I would like you guys to think about is, as you can see, it's not just visible light that comes through the atmosphere, radio waves come through the atmosphere as well. So why did our eyes not evolve to see radio waves also? Why did we only evolve to see, that's a question for you to think about. But the main point I want to make is once you get beyond visible light and maybe a tiny bit of ultraviolet, all the other kinds of light do not come through the atmosphere. So until the invention of satellites that could get above the atmosphere, we were out of luck. There wasn't very much we could do to study them. And this fleet of satellites, as you can see, is designed to do that. So if you want to observe any light that's not radio and that is not optical, you pretty much have to go to space. That's sort of the message here. Okay, real quick, if my thing will work. Okay, so one thing that I do want to, I'm sorry, this must be obvious to some of you, but it's a very important point to make, right? You might wonder, why do we need to observe light of all these different kinds, right? Why can't we just understand things? Why can't we just understand the sun by looking at it in visible light? And the answer is because all the information you need to understand any object in the sky is simply not available with any particular kind of light. And this, of course, is a, what do you call it? Folk tale from India. So many of you might have heard it already. It's the story of a bunch of people who were born blind and had no idea what an elephant was. And the story is that they were taken to an elephant, and depending on which part of an elephant they touched, they came away with a completely different impression of what an elephant was, right? So the guy who caught the tail, he thinks, oh, an elephant is like a rope. The guy who bumps into the side of the elephant thinks, oh, an elephant is like a wall. And the moral of the story is, of course, that the only way these people will have a reasonable understanding of what an elephant is if they talk to each other and they share the information they have. And this really is a very good analogy for what astronomers do, right? Light of any particular kind does not have all the information we need to understand our universe. Okay, that's the key message to understand here. Okay, and that's why we spend so much effort trying to build telescopes at every different type of light. And that was the situation until that's another representation of the fact that you have all these different kinds of light, and visible light is really only a small fraction of the kinds of light there are, right? So this was the situation until about 2014, okay? In 2014, we made the first really confident detections of neutrinos. I'll talk about them very quickly. And then in 2015, we made the first really confident detection of gravitational waves. Neither of these are a kind of light, okay? And so suddenly, humanity went from a species that studied the universe through different kinds of light to a species who can study the universe through different kinds of messengers. And besides light, we now have neutrinos and we have gravitational waves. So really quickly, what is a neutrino? Well, I wish we knew the full answer to that question, but I can tell you a few things about it. It's an extremely light, it might have a tiny, tiny, tiny bit of mass. We haven't successfully measured it. One of its key characteristics is that it doesn't interact with anything very much. That's why the cartoon there, like, you're not a snob, are you? So, just like a snob doesn't like to talk to anybody, neutrinos don't like to talk to anybody. Okay. So, and it's a fact. Sorry, it's a somewhat surprising fact. Okay, what did I do? Come on, come back. Oh dear. There we go. Can you see okay now, Anu?
Yeah.
Okay, let me escape because there's something funny going on here. I'll just share again. Go there. Let's share. Let's go back to where I wanted to go back to, which is here. And let me go to slideshow mode. Yeah. So, as you and I sit where we are sitting, about 65 million neutrinos pass through your thumbnail. They go right through the Earth and they keep going because they don't interact with anything. So this is a problem, right? Because when you say you build a telescope and you detect something, well, what does detection mean? It means that whatever you're detecting is talking to your detector. And if you have a particle that hardly ever interacts with anything, then it's very hard to detect. So how do you solve this problem of detecting neutrinos? Well, at the South Pole, this, by the way, is my old telescope. Sorry, can't resist pointing it out. Under the ice, some very smart people realized that Antarctica has this gigantic amount of ice. So there is a telescope this is obviously a drawing because you can't take a picture of something that's underground. There's a three-dimensional string of detectors, which are approximately a cubic kilometer. Okay. And because within that space of a cubic kilometer, there are billions and billions of ice molecules, right? Even though the probability, the chance of a neutrino actually interacting or talking to an to a molecule is very low, simply because there are billions of them, right? Occasionally, there is an interaction that can be detected. Okay, so this is a little bit like, to give you an analogy, right? The chance of you winning the lottery is very, very low, right? So don't waste your money on it. But if you went out and bought 1 million lottery tickets every time, then you'd probably win a lottery every now and then. It wouldn't be probably worth it because you'd be spending more money buying 1 million tickets. But you see my point, right? That's the principle here. The probability of interaction is really low. So you just enclose a gigantic volume, and then the probability becomes reasonable, and you start detecting a few neutrinos. Okay, that's just a illustration of how that works. I can come back to it. I just want to quickly touch upon gravitational waves. These are basically these are distortions in space-time. Okay. And the kinds we've detected so far, they're usually created either when two neutron stars merge or a small black hole and a neutron star merge, right? These are very, very energetic events. They're energetic enough to disturb space-time, right? So the way they're detected, I mean, at least the ones so far have been detected, is we have these two L-shaped interferometers. There's a laser going down that way, right? It creates an interference pattern. And when a gravitational wave moves through the Earth, it shifts the interference pattern by a very, very small amount. This is a true engineering marvel, right? And you deserve to have a whole different talk on it to understand like the beauty and the complexity of this. And because everyone knew that this signal would be so weak that if you saw, you wouldn't be sure if you really had detected it or not, they built two of these, right? So one of them is in a place called Livingston in Louisiana, and the other one is in a place called Hanford, which is in Washington State. And that way, if both detect something with the right time delay, then you know that you really detected something. And it wasn't like a fly batting its wing or something like that, because we are looking at an incredibly small distortion here. So, okay, here we go again. So the first detection, you could figure out theoretically that it was caused by, two objects. One was 29 and one was 36 times the mass of the sun. Given the distance, this actually happened 1.3 billion years ago. I think all of you are familiar with this idea that you've heard of the word time machine, but your eyes are a time machine because light has a finite speed. When you look into the sky, you're not seeing the sky the way it is right now, right? So even an object that's relatively close to us, like the sun, it takes about 8 minutes for light from the sun to reach us. So for the sake of argument, if you just say, let's say, the sun gets destroyed right now, something happens, okay, let's say it explodes. For 8 minutes, we will know nothing. It'll take 8 minutes for us to realize something has happened. And this is the sun, which is our closest star. The next closest star is 4.3 light years away. It's actually a triple star system, but it's 4.3 light years away. So when you look at it, you're looking at something that happened 4.3 years ago. So similarly, this object is 1.3 billion light years away. And so what happened there happened a very long time ago. It happened 1.3 billion years ago. It took that long to get to us. So remember that, your eyes are a time machine. Every time you look, you're not seeing things in the sky the way they are right now. You're seeing them the way they were a while ago, depending on how far they are. Okay, so that's the kind of pattern that you see. And if you look on the left and the right, they're the two different places. If you have very sharp eyes and you're looking very carefully, you'll see that they're not exactly the same. But, because there is an element of noise there, but they are close to being the same detection. So we're pretty confident. And what I find amazing, to be perfectly honest with you, is that years ago, when I was still in Pune University, there were some really good theoretical physicists there who were making calculations predicting what would be seen precisely when something like this happened, right? And they're just doing this purely from their knowledge of general relativity. And I find it absolutely fascinating that people can calculate these things, and then many years later, an experiment finds exactly what they calculate. So to me, it's always amazing that you can do mathematics and predict something about the real universe that turns out to be true. Okay, to me, it's not completely obvious that the universe should be so understandable, if I could put it that way. So I just, because I want to stick to my time, I want to quickly bring this to a conclusion by saying that when I first thought about giving this talk, I wanted to call light, which I've labeled EM for electromagnetic. Don't worry, this is just meant to be light. I thought I would compare it to an old, somewhat beat up car, and neutrinos and gravitational waves to two flashy new sports cars. But this is completely wrong. The real picture is more like light is like a very sturdy, reliable, and good functioning car, okay? Whereas neutrinos, which is my red baby here, and gravitational wave, which is the baby wearing a yellow hat, they're like babies. And the reason is we've only just figured out how to make these measurements. We are only beginning to understand how they can help us understand the universe. So just as when you look at these babies, you have no idea what they're going to grow up to be, okay? But you can see that they're healthy babies, and they're probably going to grow up to do something amazing. And that's really the situation we are in right now, okay? With both neutrinos and gravitational waves, another analogy that maybe to help you think about this is, imagine if the fact that you're listening to me means that all of you can hear, right? Imagine if you had actually been born without having the ability to hear things, okay? And then imagine that one morning you woke up and suddenly you could hear. Suddenly. So it would take you some time before you learned how to use that sense you got, the new sense you acquired, right? It would take you some time before you learn to appreciate music, for example, because it's a new thing and you haven't yet figured out how to use it. And scientists are kind of at that stage, okay? So we've got neutrinos, we've got gravitational waves, we have lots of cool ideas, but it's very early days. And this is why I talk about it being a revolution, right? Because this is as important, if not more important, as Galileo turning the telescope and changing the universe, our view of the universe forever, okay? And if any of you want to do astronomy, I mean, it's a great time to join astronomy because, I mean, we old guys don't know what to do, right? It's all new stuff. We have some ideas, but we have completely new tools. And I think I'll stop. I mean, I keep this slide in case somebody has a question of why are you bothering to study all this, So I think, Anu, I'll stop and take questions. I can always come back to these slides if it seems relevant to the question.
If you guys can put in your questions in chat.
While we're waiting, I had a question. What can we learn from the neutrinos that you were talking about? If we can detect them, what can we learn from them?
That's a really good question, Anu, because here's the thing, right? There are two answers to the question. One is I don't know, right? Because it's a new sense, it's probably going to teach us things we haven't even imagined. So let's say that at the beginning. But one thing I can tell you right away, remember what I said about neutrinos, that they're big snobs, they don't interact with anything. And from the perspective of someone who wants to detect it, that's a real pain in the neck. And you saw that you have to go to the South Pole and instrument a cubic kilometer of ice to be able to detect them. So that's painful. But remember that also means the following. It means that there are many places in the universe, such as the area around black holes, such as the area around pulsars, which are surrounded very often by very dense clouds of dust, of gas, of other things. And normal light, has trouble getting through. The clouds are blocking off the light. Well, guess what? Neutrinos come right through them, right? Because they don't interact with anything. So one thing that we can really count on is we can use neutrinos to study very dense and obscured portions of the universe, which you can't do with light because the light gets absorbed or it gets scattered or something happens to it. It doesn't come to us, right? So we can pretty much count on that. I can give you an example of that. That a photon, a particle of light created at the center of our sun, it varies, right? There's a distribution, but it can take many years for a photon to emerge from the center, start from the center of the sun and actually reach the surface and escape. But it takes a neutrino created at the center of the sun only a few seconds to come out. And because it hasn't interacted with things on the way, the neutrino is still carrying the information without having corrupted it or lost it, right? An analogy that you can use here is, imagine if there are two people in a very crowded hall in your school, and they're both given the same message to carry to somebody at the other end of the hall. One of them is a snob, doesn't talk to anybody, puts his head down and just runs across the way and delivers the message. The other person is a very chatty, friendly guy, and he stops and talks to everybody. So by the time he gets to the other end of the hall, he has already forgotten the original message, right? So that's sort of the difference. The neutrino is the guy who doesn't talk to anybody, just goes shh. And if you catch him, you get the message that, relatively clean and pure message.
Like, what skills do you think are required for your job?
So that's a good question, right? So when I was a child, I'd never met an astronomer till I went to Pune. But people had already told me that, oh, if you want to study astronomy, you have to be very good at math. That is true. Okay. And they also said you have to be very good at physics, which is also true. Okay. What they didn't say, and what I will add to that, is I think you have to be pretty good at least using computers effectively. Right. So having said that, there are specialized things in astronomy. So for example, if you can do something called astrochemistry, where it really helps to know a lot of chemistry. As you guys also know that as recently, the first planet that is not circling our sun, the exoplanets, right? The first one was discovered as recently as the mid-90s. But now we know of more than 5,000. So, if you go, NASA maintains a list of known confirmed exoplanets, and the number exceeded 5,000 like late last year. I don't know exactly the number today. So, as we learn more about these, as we discover more exoplanets, and, the James Webb Space Telescope is already able to look for evidence of some elements in the atmospheres of these, some of these planets. And one of NASA's next major telescopes, it doesn't have a formal name yet. NASA usually doesn't have a formal name when they start developing a telescope. They only have a working name. And then eventually, once it gets launched, it gets a formal name, right? So the Fermi Gamma Ray Space Telescope that I told you about, it used to be just called GLAST, which is an acronym. So anyway, the next big telescope likely is going to be something that is now being called the Habitable Worlds Observatory. So we seem to be moving in the direction where we might be able to start looking more seriously for life in at least in the planets in our solar system, right? So there's room for people who are biologists. There's astrobiology. And also, I mustn't forget to mention geology, right? Because if we get, like, for example, if you go to Mars, well, you want to explore Mars, one of the very important experts you need is people who understand geology, right? So, yeah, there's an element of specialization there, but I would say that having a really, really good background in mathematics and computer science is probably good across the board, right? And then depending on your interests, you can do geology, you can do chemistry, you can do biology, right? Yeah. So I guess that's the answer I would give.
Yeah. Do you have any advice for like people who would like to pursue in like the fields of like astrophysics?
So one thing that I like telling people is that astrophysics is easy. It's really more important. So, like instead of going and studying astrophysics, it's more important to get your math, your basic mathematics and your basic physics and basic computer science strong. Because if those are strong, then astrophysics itself is not very difficult. At least that's what I think. And one thing I should say, which I think is extremely exciting, is astrophysics is one of the very few sciences I know where almost all the data that we get, right, the professionals get, is available to everybody very easily. Okay. As long as you have a decent internet connection, you can, so for example, again, the Fermi Gamma Ray Space Telescope, we get data, every day, downloaded every day. Someone looks at it to make sure that it hasn't been corrupted or something bad hasn't happened. And then usually within 24 hours, the data is on a public server. Okay. So, and I don't know many sciences where this is true, that if you actually, and not just the data, the software that you need to analyze the data is also publicly available. And if you have any trouble installing it, there's a help desk that will happily answer questions, okay, and help you install it. So I don't know many other sciences where it is true, but if you have enough time and dedication, you can do cutting edge research from your home almost without any sort of, and I know people, for example, who wanted to be an astronomer when they were children, but didn't, and like had some other career. As they are retiring and they have more time, they are actually coming back and being able to do serious astronomy, not just like, amateur. And this capability is going to get even better because our long-term goal is to move most of the data into the cloud and also put most of the software that you need to reduce this data as Jupyter notebooks next to in the cloud as well. So, you can sign up, get an account for free, and within reason, you can go and you don't even, so basically, because, the data volumes are increasing. So downloading data to your computer is, will probably get harder with these very large data sets, but you can just get an account, which will be free, and you can go onto the cloud and do all the computation. And I don't know any other branch of science where you can do cutting edge research with the same data that the professionals are using. So that can be pretty exciting, I think.
So what made you interested in astronomy and like choosing to go into it?
Anu, you're asking the best questions. Okay. This is a mildly embarrassing story, but okay, it should, I might as well tell it. My wife always makes me tell this story. As you know, I grew up in Darjeeling. When I was about 5 years old, my uncle some guy came to visit my uncle, and he was a palmist, I guess. So, he was reading my uncle's hand. I, of course, didn't know what was going on. I asked my mother what's going on. And my mother said, some people believe that you can read the future by looking at lines on somebody's hand. And so I asked my mother, I mean, that sounds quite interesting. What is it called? So my mother said astrology. Okay, she didn't say palmistry. She said astrology. And there's a bookshop, which is still there in Darjeeling. And I learned to read pretty early. And my parents had an agreement with the owner of that bookshop that I could just go and get any book and they would send the bill at the end of the month. So I went, because I got excited about this, I went to the bookshop looking for a book on astrology. Okay. But I guess my spelling was not very good. So instead of picking up a book on astrology, I picked up a book, which I still have, called Astronomy. Okay. In this big block letters, and I suspect, I don't remember exactly, but I suspect that I didn't really understand everything that was written in the book, but it had the most amazing photos. I still remember the photos, right? Like beautifully illustrated book. And I just got hooked. And like, I asked my mother, like, what is this? What do I have to study? And that's how I told you. My mother just told me, I believe you have to be good at math. And I believe you have to be good at, and I stayed faithful to that. I always stayed at, that fixed me, that made me do so. My grandfather used to make fun of me because he said, like, you knew what you wanted to do when you were 5 years old. And apparently my father was the same. He knew he wanted to be a doctor when he was a little child, and he never changed his mind. So in some ways, we are boring people. We decided very early what we wanted to do, and we just stayed with it. Yeah, so that's the story. So sometimes not being able to spell properly helps you.
I have a question.
Sure.
So, I like you just talked about how when you were getting into astronomy, like you saw pictures of like, were there like nebulas that were like found through natural light with nitros and gravitational waves? Do you think any type of like art could similar like from natural light be found through those new ways of technology?
This particular book, the astronomy book that I bought by accident, I remember that they had, for example, extremely good drawings of the sun and solar prominences and solar flares. And they turned out to be remarkably accurate. We've learned a lot about the sun since this book was published, right? And it's impressive to me that it's hard for me to look at that book and say, oh, this is wrong. You know, the sort of basic idea they had was actually pretty good. Neutrinos are different, right? Because look, with light, right, especially with optical light, we have we see light around us. We have some sort of sense of how to interpret them. With neutrinos, we are completely outside our comfort zone. We sort of have no good sense of how to even picture them. And I like very much watching or hearing artists trying to interpret them. But, you know, you have to remember that art is art. And even if it's attractive, we don't really know if, you know, how close to reality it is, even if we enjoy it. And in this context, I'll go back to my statement about mathematics. So what's fascinating to me is that mathematics is able to describe things. Now, not everything that mathematics that you get out of math applies to the real world, but a lot of it does. And that's the thing that I find very, very fascinating, right? Like, so you guys probably know the story of Dirac, right? He came up with the equation that describes an electron, but his equation had two solutions. And so, you know, he sort of said, well, you know, we have this particle with a certain mass and a negative charge. But if you look at the equations, there appears to be a particle with the same mass, but a positive charge, right? And then after he did the theoretical calculation, people went and discovered the positron. And to me, that's utterly fascinating that somebody just like is doing some calculations on paper and comes up with the idea that, hey, there might be a particle with the same mass, different charge, and then somebody finds it, right? And in the same way with both gravitational waves and neutrinos, people worked out the mathematics and predicted that there could be such a particle with such properties. And I mean, in gravitational waves, by coincidence, they were discovered in 2015. They were predicted by Einstein first in 1915, exactly 100 years before. It was a very nice coincidence, right? And to me, that is utterly fascinating that somebody sitting and doing literally calculations on pen and paper with pen and paper makes a prediction, and 100 years later, we find what he predicted, right? So in that sense, mathematics to me is like the highest form of art, because, you know, it brings out both the beauty and the truth that's hidden in the physical world.
In the future, assuming that we can detect like individual gravitron particles, what would be the benefit of that over neutrinos?
That's a little bit like asking me, what is the benefit of hearing something as opposed to seeing it?
Oh, okay.
Right? Because you're talking about two completely different messengers, right?
Okay.
I think the way I see it is they're complementary. It's like two different, like, you know, that picture I showed you of the elephant with the blind men, right? It's like two blind men, they're detecting completely different things. And the most useful thing you can do is you can bring that knowledge together. You can bring that information together, and that'll help form the bigger picture.
Okay.
Yeah.
Thank you.
Sure.
Okay, I have one question. I was wondering what you thought was what is JWST telescope's like biggest accomplishment in terms of like discovery and like neutrons and stuff like that?
Well, that's an easy question to answer. The most important discovery of the James Webb Space Telescope has definitely not happened yet, right? It's only been, it's only just really started observing. And to me, I mean, okay, so this question is very biased, right? Because it sort of depends on what you're interested in, right? Because it's an observatory. It's observing everything from exoplanets to, you know, different types of nebulae to AGN. So the answer depends very much on who you're talking to, because it's whatever they're interested in, right?
Yeah.
Yeah. So and I have absolutely no doubt that most of its best discoveries are yet to come. Having said that, to me, for the moment, the thing that I got most excited about is the possible detection of, you know, features in the exoplanets, in the atmospheres of exoplanets.
Oh,
I mean, think how cool it is, right? Like, I mean, okay, firstly, back in 1990, 95 or something, you guys, most of you weren't, I mean, you guys were probably not even born yet. So anyway, but we were just very thrilled to find any exoplanets. Okay, it was very, very exciting. But now in 2023, when we know like 5,000 exoplanets, it's still exciting to find more, but we know 5,000. Okay, so it's like the more. So now we moved on to this idea that, oh, wouldn't it be great if you could find signs of life? But these are really far away, right? So what we're trying to do is find signatures of compounds and elements that would be in the atmosphere, or which, at least on Earth, we know that these particular compounds are created by living organisms, right? But this is a tough game to play, right? Because, you know, even if we found it, right, even if we found certain compounds that are typically produced by living organisms, we can't be sure that they're created by living organisms, right? Because there could be some physical or chemical process, naturally occurring process, which could create them. But at least we would get pretty excited because at least there would be a possibility.
yeah.
Yeah.
Mhm.
Yeah, but asking somebody like, you can ask somebody what is your favorite result from the James Webb Space Telescope, but
Yeah.
you'll get a different answer depending on who you talk to, right? It's what you're interested in.
All right. Thank you.
Sure.
So is there any relation between astrology and astronomy? Any connection at all?
Well, so I want to be very, very clear, right? When you look at the origins of astrology, right, they start together because, and it's perfectly understandable that people would have some sort of belief that stars would have an effect on their destiny. It's easy to understand that because, I mean, the sun clearly had an impact on them, right? Also, depending on where you lived. So, for example, the Egyptians, whose entire civilization depended on the flooding of the Nile River, right? They learned over the years that when certain star was rising, in the morning from a certain part of the sky, the Nile was about to flood. This was very useful information to them, okay? And it's not surprising that they thought that somehow the star was responsible, right? So the basic idea that, like, okay, so the stars could have an impact on people, it's not unreasonable to begin with. But we have learned a lot since then. And we know for a fact, right? There's absolutely no doubt. And I'm sorry if I'm insulting somebody inadvertently, right? Because, I was talking to my sister yesterday and about something strange that was printed in a newspaper in India, the Hindustan Times. And she was saying, oh, this is a reputable newspaper. How come they're printing this? And I said, look, so many respectable magazines and newspapers have horoscopes. And to be blunt, that's complete rubbish. What are you going to do? Right? If you live in a democracy, one of the rights you have is you have a right to make a fool of yourself. They didn't write that explicitly in the Constitution, but that's what living in a free society means, right? So no, there's no scientific basis to astrology. All I'm saying is that back when people, started studying the sky, I can understand why people thought like that, right? I mean, just like if there are still people today who insist that the Earth is flat. Okay, I can understand when people did not have much of a knowledge. If people hadn't traveled that much, you look around you, then the world looks flat. It's not unreasonable to think that, right? But once people started traveling, once they started observing things, it became very clear very quickly that it's not flat. But yet, even today, if I go at at this meeting of the American Astronomical Society, I still have people come and argue that no, the world is still flat. So, I mean, some things are understandable. They were understandable, centuries ago. Today, they're not.